Okay, so we have already seen the idea of automorphisms of fields. We have also seen that if a group of automorphisms is given to us of some field, then the notion of the fixed field for that group, and also the group of automorphisms of a field relative to a base field. By definition, it's the group of those automorphisms of that given field which fix all the elements of the base field. Now today we are going to see these ideas illustrated in 3 examples. Now before we see the examples though, let us see a simple idea. It's an observation actually. Suppose that K is a field of characteristic 0. And in fact, let us remember that the fields we are considering all have characteristic 0. Now, a property of such fields is that in any such field, there is a copy of the system of rational numbers. More rigorously put, this means that K has a subfield that is isomorphic to the field of rational numbers. That is, there exists a subfield E of K which is isomorphic to Q, the field of rational numbers. Now, what does it have to do with automorphisms? Say G is a group of automorphisms of K. Then we know that G has a fixed field. Suppose that fixed field is E. I have already taken E to mean something else. Let us give it some other name, say we call it L. So this is the fixed field of G. So by definition, this is the set of those elements in K which are fixed by every element of G, which means that after all L is a subfield of K. So being a subfield of K, a field of characteristic 0, L also has characteristic 0, which means that L has in it, just like this thing, a copy of the field of rational numbers. Or more simply put, the rational numbers are there inside L. So that means if you now take any sigma in G, then sigma, because it fixes all the elements of L, will in particular fix all the rational numbers as well. That is, R sigma is going to be equal to R for all rational numbers R. And this is going to be the case for any field that we consider. Okay, this is one observation, that any automorphism will actually, you see, G is a group of automorphisms. What group this exactly is, that is not our concern. G is any subgroup of the group of all automorphisms of K. So from that we are getting a fixed field which is also some subfield of K. This will depend entirely on what G actually is. But whatever the case is, all such fixed fields are going to contain all the rational numbers. So regardless of what automorphism we are choosing from G, that is going to fix all the rational numbers. So the ultimate conclusion of all these things is that if your field has characteristic 0, which is going to be the case, okay, for us, then any automorphism of that field will keep all the rational numbers fixed. This fact will help us determine automorphisms of fields. Now let us start the examples. What we will do in these examples is this. We will consider a field f and an extension of that field k, and we will calculate this group, the group of automorphisms of k relative to f, and in each case we will also see what the fixed field of this group is. That's what we will see in these examples. Now in this first example, our base field is the field of real numbers and the extension is the field of complex numbers. We already know that C is an extension of R, and that too with a finite extension of degree 2. Okay. Now if we take any automorphism sigma in this group, what kind of function will sigma be? To see that, let us take any element in K, which is going to be a simple complex number, and apply sigma on it. Because sigma is an automorphism, this will be A sigma plus B sigma I sigma, because sigma preserves both addition as well as multiplication. Now keep in mind that sigma needs to fix all the elements of f, that means all the real numbers. So A sigma is A and B sigma is B. Now everything depends on what I sigma is. To see what it can possibly be, you calculate the square of I sigma. Because sigma respects multiplication, this will be I square sigma. Now I square sigma, I square is minus 1. And the sigma image of minus 1 is going to be minus 1 itself. Alright. Why? That's because minus 1 is a real number and sigma is supposed to fix all real numbers. Or you can use this fact also, because minus 1 after all is a rational number as well. So anyway, it's going to be minus 1 ultimately. Now note that since sigma is a, let me show it here, sigma is after all a mapping from k into k. So that means I sigma, whatever it is after all a complex number whose square is minus 1. So that means there are exactly two possibilities for I sigma. It is either I or it is minus I. Now because everything that sigma does to A plus Bi now entirely depends on I sigma, so accordingly there are precisely two possibilities for sigma itself that comes from these two cases. In the first case we get this. And to distinguish between the two functions, we are going to call one of them sigma 1 and the other one sigma 2. Here this will be A plus B I. This time we are taking I sigma equal to I. So that means sigma 1 is the identity function, which is also an automorphism, we already know. However, sigma 2 will be something else. This time I sigma is minus I. So sigma 2 is your well-known complex conjugation function, and it follows easily. I mean, one can verify that both of these are actually automorphisms. Note one thing carefully, that we have assumed sigma to be an automorphism, and then we have got these two possibilities. That does not automatically mean that these two are automorphisms. You have to verify that separately, but once you do, you see that they are automorphisms. So that means in this case G is G means this thing has two elements in it. That is, the order of G is 2. Now let us see what the fixed field of this G is. Now a general group of automorphisms will have some fixed field. However, here something about the fixed field is there that we already know. You see, we are only considering those sigmas that fix the elements of F. So already sigmas fix all the real numbers. So all the real numbers belong to the fixed field of G, fixed field of the group G. But are there more elements in the fixed field? Let us see. Suppose A plus Bi belong to K, and it is an element in the fixed field of this group, because the fixed field after all is going to be a subfield of K. An element in the fixed field of this, which means what? It means that this element is going to not be changed by any element of G. So it won't be changed by sigma 1, which is not surprising, because sigma 1 anyway does not change anything at all. It's the identity mapping. However, sigma 2 also should not change A plus Bi. We will get something from this. So if we apply sigma 2 on A plus Bi, then we are supposed to get A plus Bi itself again. However, what does sigma 2 do to A plus Bi? It gives us A minus Bi. And this implies what? This implies B2, well, why did I write B2? B should be equal to 0, which means what? It simply means that A plus Bi is a real number, and this shows that not only are all real numbers in the fixed field of G, but that's it. We do not have any non-real complex number in the fixed field. That means the fixed field of this is F itself. Note carefully that this group is abelian, having order to its abelian, and that to its cyclic. It's generated by sigma 2. Okay, now let's see the next one. In this next one, our base field is the field of rational numbers, and the extension we are going to consider is this. That is, we are adjoining cube root of 2 to the field of rational numbers, where this of course means the real cube root of 2, which you know from analysis that it exists. The real cube root of 2. Now you also know that the degree of this extension over Q is 3. What does it mean? It means that as a vector space over Q, this field has a basis of 3 elements, and in fact this is a basis. 1 cube root of 2 and the square of the cube root of 2. We have already seen these things, okay, when we studied extensions, finite extensions, bases, those things. What does it mean? It further means that the elements in K are going to all be linear combinations of these basis vectors, which means that they will look like this: alpha naught plus alpha 1 times this plus alpha 2 times square of the cube root of 2, where alpha naught, alpha 1 and alpha 2 are going to come from the, they are scalars, they are rational numbers. You can write F or Q as same thing, they mean the same thing. Okay. Now in this case, also just like that previous example, what can be an automorphism of K that will fix Q? Well, in this case you see, even if you do not consider automorphisms fixing Q, but because of that property, any automorphism of K has to fix Q. Okay. So anyway, let us take sigma in G K comma F now, and let's see what that sigma does to this. So if you apply sigma to this, you will get, let us first write all the things in detail and then we will figure out. See, in order to minimize our writing effort, we sometimes are tempted to skip steps, but that's a dangerous thing to do. It's always better to write everything and then only see what those things ultimately become. So sigma is supposed to fix all rational numbers, so this is alpha naught, alpha 1, this plus alpha 2, because sigma will go inside, sigma respects multiplication, so we get this. So just like the previous example where ultimately everything depended on I sigma, this time everything depends on what sigma does to the cube root of 2. To figure that out, we considered this fact. If you take the cube of the cube root of 2, you are going to get 2. So that's why if you take the cube of this sigma image of the cube root of 2, then that is going to be this, because sigma respects multiplication, and then this will be 2 sigma because 2 is rational, so this will be 2, which means that cube root of 2 sigma itself is also a cube root of 2. However, now note this thing, that although we have gone outside of the field of rational numbers by adjoining this irrational number to cube, but we are still inside the field of real numbers. All these things are happening within the system of real numbers. This means that this is a real number whose cube is 2. That means it's a real cube root of 2. Okay. And that is why, there is only one cube root of 2, one real cube root of 2. Had it been square root, there would have been 2. However, due to the oddness of 3, there is only one real cube root of 2, and which is this itself. So that means this is nothing but the cube root of 2 itself. And now we use this fact here. What do we get? We just simply get back the original input, because this is not changing, nothing is changing ultimately. Which simply means that sigma is the identity map. That is the only possibility in this case. So here this consists only of sigma, which is the identity map. Now can you see what the fixed field of this group will be? You see, because it is the identity map, it is going to fix all the elements of K actually, right? So what does that mean? It means that the fixed field of this is K. The entire extension, cube root of 2, the entire extension is the fixed field. So here you see, there what we had in the first example, there the fixed field was the base field itself, the smallest one possible. Here however, it is the largest field that can be considered in this case, namely the entire field, the actual field. Let us now see the third one. In this case, what we are going to consider is this. Again, F is the field of rational numbers. Here also we are going to get one extension by adjoining something. But unlike this one, we are not going to adjoin an irrational number, but a non-real complex number. K is F omega, where omega is this, which means nothing but this, plus I sine 2 pi over 5. So that means it's a fifth root of unity. It's not 1, okay, it's other than 1 because these are non-real. I mean, this is not 0, so it's not real. However, we already know something about omega. One of the things is obvious, that the fifth root of omega is 1. The fifth power of omega is 1. And there is one more thing. Omega satisfies the polynomial Now, if one applies the Eisenstein criterion, which we have seen in our study of ring theory, on this polynomial, then one gets the fact that this is irreducible over the field of rational numbers. Now, because omega satisfies omega satisfies x to the power 5 minus 1 also, but this is a lower degree polynomial, but at the same time it's non-trivial. That omega satisfies, and at the same time, because this polynomial is irreducible, this is the minimal polynomial for omega, and that means that the degree of this extension k over f is 4, the degree of the minimal polynomial. What does that mean in turn? It means that as a vector space over f, k has dimension 4. So it will have a basis of 4 elements. And that will give us the general form of the elements of k in terms of the rational numbers. And this is nothing but just this. I mean, this is a basis of k over f, 1 omega square omega cube. We already know these things from field extension theory. So that means the general element of k will look like this. Where these are rational numbers. Alright. So what is our aim? Now our aim is same. We are going to calculate the group of k relative to, group of automorphisms of k relative to f. So let sigma be an element in that group. So let's see what sigma does to this general element. Yeah, now that we have seen this type of calculation twice already, we can be a little sketchy and skip some steps. But again, I am saying, whenever you do something like this, you have to make absolutely sure that what you are doing is correct. Omega sigma plus alpha 2 omega sigma square plus alpha 3 omega sigma cube. So again, everything now rests on omega sigma, the sigma image of omega. And this is in fact always the case when we get an extension by adjoining something to the base field. You bring in some foreign object, you then have to say what that object does, where that object is taken by that automorphism. Okay, so that will depend, that will decide what the automorphism ultimately is going to be. So again, we look at these things. This is a relation that omega satisfies, so we can use this relation. Because sigma is an automorphism, sigma is a homomorphism of the multiplicative group of the field, and that's why 1 sigma is equal to 1. Sigma maps the identity element to the identity element, or simply because 1 is a rational number, so sigma fixes 1. Alright, so omega sigma also has to be a fifth root of unity, just like omega. However, omega is not the only fifth root of unity. We know that there are precisely 5 different fifth roots of unity in the field of complex numbers. All these things are after all inside the field of complex numbers, and this is one of them. But we already know something else as well. Since omega is not equal to 1, so this is not equal to 1 sigma. Why? That's because sigma is a one-to-one function. Being an automorphism, it's one-to-one. So distinct inputs are going to give you distinct outputs. So whatever this omega sigma is, whatever fifth root of unity it is not 1. So that means it can be one of the other 4, which we already know are these: omega, omega square, omega cube, and omega to the power 4. And that gives us 4 possibilities for the automorphism sigma. Parts of this example are exercises. These claims, that this polynomial is irreducible, so the degree is 4. These are exercises that we will see when the section is over and we start solving the exercises. There we will see how these things are actually handled. Right now we are going to take these things for granted. So in general, sigma, depending on what this thing is, what omega sigma will be from among these 4 possibilities, in general sigma will look like this for I equal to 1, 2, 3, 4. So we accordingly, to distinguish the possibilities, we denote sigma I. Okay, we use a suffix. So there are 4 such functions, and it turns out that these are 4 automorphisms in this group. I mean, they are all the elements of this group. That is, this group now has 4 elements. So again, it is abelian, but something else is also true. You can understand, of course, that here from this description of these functions, sigma 1 is nothing but the identity function, identity automorphism. So that is the identity element in this group. But there are some relations that these functions satisfy, which are these. The fact that these are actually automorphisms is an exercise. This is exercise 4. We are going to have to prove this thing there. We will do it. Now here we have some relations. It turns out that the square of sigma 2, you can verify these things, okay. This is sigma 4. The cube of sigma 2 is sigma 3, and the fourth power of sigma 2 is sigma 1, which means that every element here is some integral power of sigma 2, and that is why this is not just an abelian group, but in fact a cyclic group of order 4. And the fixed field of this group, that is the next thing the way we are considering these things, that is the next thing to consider. The fixed field, it turns out, is F. In this case it is not K, it is F. And in fact this is exercise 5. Something else also the author says. I leave the verification of this fact to you. There is a subgroup of this group, which is this group, consisting of sigma 1 and sigma 4. Sigma, you see, if you use this one and this one, it turns out that sigma 4 has order 2. So it generates a cyclic subgroup of G of order 2. Now for this group of automorphisms, also there is a fixed field, and that fixed field looks like this. The fixed field of H is this. And it is it is also an extension of F. It's going to be an extension of F, and it's an extension of degree 2 of F. So this last part I leave to you to prove. Now finally, before we end this discussion today, you may think, looking at these examples, that these groups that we are getting are going to be cyclic, but that is not true. In general, these groups are not even abelian. And you have also seen something, so that raises the question of why then the author has chosen these examples in which we do not see any non-abelian group. It's because these examples are simple, but at the same time, these examples also show one more thing, namely that for some extensions of F, the fixed field of Gk, F is F, for example in this case, and in some cases it's not F. So those extensions where the fixed field of the group of automorphisms of that extension is the base field, they are special. They are called normal extensions. Their properties are going to be crucial for us in Galois theory. So, but anyway, that's just it for tonight. Our next upload, of course, is on coming Tuesday. So see you on Tuesday. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.